Okay, so yesterday we had left off on this equation here, 4 to the x power times 2 raised to the x squared equals 16 squared. And we were trying to solve this. And at the end of the class, I had gotten stuck because I knew something was wrong and I couldn't see the error in my work. Sometimes when you're looking at your own work, it's hard to see that. Sometimes it's hard to see it when you're grading somebody else's work. But anyways, right here, once I saw where the error was, I was like, duh. Anyways, right here, same base. We add our exponents. I had multiplied our exponent. And so in this case here, this should have been this 2. I'm gonna rewrite it so that the x squared is first. This should have been x squared plus 2x. Okay, so that changes this. And so from this point, our goal was to manipulate all of this so that the bases were the same and that we had only one exponential function equal one exponential function. And once we got that, then we could rewrite it so that we're just setting the exponents equal to each other. And so from here we can say, well then x squared plus 2x has to equal 8. And so it's a quadratic equation. We're going to solve that quadratic equation by setting it equal to 0. So we have x squared plus 2x minus 8 equals 0. It's factorable, so the two numbers that multiply to give us -8 and add to give us +2, or +4 and -2. So x would equal -4, or x is equal to 2. So it's the set of numbers -4 and 2. And so I had seen that answer right when class was over. I think we were running a little bit late, and I noticed that my answer was wrong and there had to have been some error in there. Okay. So we were just looking at exponential functions, solving exponential functions. So right now we could only solve exponential functions that we can manipulate the bases to be the same. Our problem is if we can't manipulate the bases to be the same, we're trying to solve for variables that are in the exponent. And so this is where logarithms come in. And so yesterday when we were graphing exponential equations, you might have recalled that I said that this is a one-to-one function. It passed the horizontal line test, and so therefore it must have an inverse function. We were talking about inverse functions yesterday too, and the properties that have to hold in order for a function to have an inverse. So logarithms So we were looking at yesterday y equals b raised to the x power. We said that there was 2 different shapes that you could get pertaining to what b was. There are some stipulations on b. In order for this to be an exponential equation, it could not be 1, and b had to be greater than 0. If b was greater than 1, we saw that our graph looked like this. We also had a horizontal asymptote at y equals 0. We saw that if b ended up being between 0 and 1, so it was a fraction that was less than 1, but greater than 0, the graph was reflection. It ended up, and we talked about y, this was reflection, but it was reflection across the y-axis, and the shape looked like this. And so again, we said that functions that were one-to-one had an inverse function. And we talked about how to solve inverse functions, and we did that by swapping our x and y values and then solving for y. And so if we try to find the inverse of y equals b raised to the x power. Okay, so again, we swapped our x and y value, so we would rewrite this as x equals b raised to the y power. So again, I mean, if we could manipulate these bases to be the same, I could tell you what this y, or I could solve for y here, but without these bases to be the same, and I can't, there's no way I can get this by itself right now, y equals. And so this is where they came up with a definition. And so by definition, they're going to do it this way. So by definition, if you have y equals log base b of x is the same thing, they're identical, as x equals b to the y. So logarithms, basically, you're trying to figure out what can we raise this base to. It's basically our answer is always an exponent. What is the exponent of this base that would give us back this x value? So a couple other things that we know about this without even kind of graphing or solving any problems right now. We know that if a function and is an inverse of one another, we know the composition of the two, we have to get back x. We also know that the domain and the range of a function and its inverse are swapped. And so we could pretty much even get the graph of what these, this is without even knowing much about it. Anyways, this here, when we were looking at exponential functions, notice that our domain is all real numbers. So the inverse, which is our logarithmic function, well, we were swapping x and y values to get our inverse function. And so we discussed that this was the range of the inverse function. So our range of a logarithm, we're going to hit all of our y values. Our range is going to be from negative infinity to infinity. If we looked at the domain of our exponential functions, there was no restrictions on x, our exponent. We can plug any number, any real number in there and get back a real number. There was, so that was our domain, but our range, any number we plugged in here for x, we always got back a positive number. If we plugged in a negative number for x, by rules of exponents, that just brought it down to the denominator. B was always positive, so 1 over a positive number is positive, and it's getting closer to 0. And so our range for our exponential function, it was getting closer and closer to 0, but not ever touching the x-axis, so it's from 0 to infinity. And that has to be the domain of our log function. Zero to infinity. Okay, which kind of makes sense. Notice here our base had to be greater than 0. Our base has to be greater than 0. Actually, no, that doesn't make sense. But our base does still have to be greater than 0, and b can't be 1 for a logarithmic function. So if we have f of x is equal to b raised to the x power, then we just found that f inverse of x is equal to log base b of x. So before we start graphing logs, let's just go back and let's look at, by definition, again, rewriting a logarithmic into an exponential is kind of helpful in order to figure out what your exponent is. And we can kind of use rules that we were just using for exponential equations to solve these. And so let's say, let's pull some out. So none of these are, okay. So find the exact value of each logarithm without a calculator. And so let's say we have log base 8 of 8. So technically what this is saying is we're looking for something. And that something that we're looking for is what we can raise our base to get back 8. Well, these are the same base, so we can use the rules of exponents that y then equals 1. So really we could go through this. If you understand the definition, you're looking at your base and thinking to yourself, what can I raise 8 to get this up here back, which is 1. So if we have log base 7 of 49, so you're thinking to yourself, what can I raise 7 to? 7 to what is going to give us back 49?
The second?
Yep. So this would equal 2. And we can prove that by what we were doing before, manipulating these to be the same base, then y equals 2. If you have a log and the base is not shown, so let's say you have a log of, and then it just shows the square root of 10. If the base is not shown, it's known to be base 10. So no base shown. Then it is base 10. So same kind of idea, but this time we're thinking 10, because our base is 10. We're going to raise to what gives you back the square root of 10. So this is where it's helpful to remember that we can rewrite radicals as rational exponents. So square root of 10 is the same thing as 10 to what power? 1/2 power. So 10 to what power gives us back the square root of 10 is just a half. So if you had just log of, let's say, the cubed root of 100. So again, our base isn't shown in this one, but if it's not shown, we know it's 10. And so we have 10 then raised to what power would give us back this cubed root of 100? So we need to manipulate this. So this is 100, right? Raised to the cubed root is 1/3 power. I'm just going to keep bringing down my 10 to the y. This is not exactly the same. We need to manipulate them to be the same base, but 100 is the same thing as 10 squared. So 100 is 10 squared, and that's raised to the 1/3 power. And then power to power, the rule is multiplication, so we get 10 to the 2/3 power. So log of the cubed root of 100 is equal to the exponent, which is 2/3.
So the answer for these would be 1/2 and 2/3, and not 10 to the 1/2 and 10 to the 2/3.
Right, right. So yeah, so right here I could have gone one more step. Y equals 1/2. And over here I could say y equals 1/3. So it's always, we're always, the answer, well, if our unknown is on this side, our answer is always the exponent. So what about log? The base is the square root of 3. And we have 9. So this is saying, okay, what can we raise this root 3 to? So root 3, we're going to raise it to what? And that's what we're trying to figure out to get back that 9. So we want to use our rules of, we can manipulate bases to be the same, then and exponential equal an exponential, then we can set the exponents equal to each other. So I notice 9 and square root of 3 can both be manipulated to be base 3. And so here we'll have 3 raised to the 1/2 power times y is equal to, and 9 is 3 squared. So power to power is multiplication. And so we have 3 1/2 y, or y over 2, is equal to 3 squared. And so y over 2 then has to equal 2. And then we see y then is 4. So our answer is 4. So we can check it, right? This is saying root 3 to what power? And we said it was 4, would give us back this 9. Well, I know that I'm multiplying this out 4 times. That's one way you can think of it. We could rewrite that square root as a 1/2 power and power to power. You'll see 1/2 times 4 is 2, 3 squared is 9, or by definition, Square root of 3 to the 4th power is multiplying root 3 by itself 4 times. This is 3. Square root times square root of the same thing is the same thing. And 3 times 3 is 9. Okay, so hopefully that kind of came back to you. So find the domain of the following logarithmic functions. Okay, so when we were dealing with exponential functions, we don't have to worry about the domain. Any real number would work. But we saw that that changed, swapped our domain and range, and our domain for logs had to be our range of exponential, which was 0 to infinity, not including 0. And so when we're looking at these log functions, let's say g of x is equal to, let's just do log of x minus 1. So you can only take a log of a positive number. That doesn't mean my answer can't be negative. It just means I can't take the log of a negative number. What did I just say? You can only take a log of a positive number, which just means the same thing. And so in this case, then, I know what I'm taking the log of in this case, which is the x minus 1. This x minus 1 then has to be greater than 0. So it's a linear inequality, and so we do that and solve them similar to linear equations. Get x by itself, add 1 to both sides, we get x is greater than 1. So our domain are all numbers, 1 and not including and greater. So what if it was g of x is equal to 8 plus 5 log of 2x plus 3. So the only thing that affects the domain, this 8 in here does not affect the domain. It has to do with our log. And so only place that we would have troubles are variables that we plug in for x that give us a negative number and what we're taking the log of. And so again, you would just set what you are taking the log of. In this case is 2x plus 3 has to be greater than 0. So subtract 3, 2x is greater than negative 3, divide by 2, x has to be greater than negative 3 halves. What if it was log base 3 of a rational function x all over x minus 1? Okay, so can't take a log of a negative number. And we would have problems when our denominator is equal to 0. So x all over x minus 1 has to be greater than 0. So we solved rational inequalities differently than linear inequalities. We could look at the graph of them and determine where this was above the x-axis, or we can look at our critical numbers and test on each side of a critical number. So values where it would change would be either where our x-intercept was on our graph, which is at 0. So critical number is when our numerator is equal to 0. And it also could change direction on our graph across a vertical asymptote. And this has a vertical asymptote at 1, or a critical number is what sets our denominator equals 0, which is 1. Okay, so if we tested numbers on either side of this and we plugged it in, we want to see, do we get a true statement or a false statement? If we get a true statement, then any number on that side would work. If we get a false statement, any number where that was would not work. Okay, so if we choose a number less than 0, because 0 is a critical number, so let's say -1. Again, I'm only worried about the sign of what the result is. I don't care really what number I get back. The sign will tell me if it's true or false. So my numerator is negative all over a -1 minus a 1. That's a negative. This is greater than 0. So any number to the left of 0 would be part of my solution or part of my domain. So choose a number between 0 and 1. So if you chose maybe x equals a half, if we plug this in here, so we have a half, which is a positive number, all over 1/2 minus 1 is a negative number. This is less than 0, so this is a false statement. Any number you chose in between there would not work. Last but not least, choose a number to the right of 1. So if x is equal to 2, plug this in here, we have a positive over a positive, which is greater than 0. And this is true. So our domain, we could use any value of x, which is from -infinity to 0, not including, could be clues, not including 0 because it's strictly greater, union from 1, not including 1, to infinity.
So you put x is not equal to -1. Wouldn't that just be 1?
I'm sorry, I meant to put 1. You're right, 1. It's 1 that makes this 0. I was thinking x minus 1 equals 0, but decide not to go through that route. Natural logs. Logarithms. Are base E. And it's written ln of x. Okay, so I normally, but I noticed, or I've been told multiple different semesters, I normally do a lowercase l, but people have thought that has been a 1. So maybe I'm going to do it capital L now. So ln as natural log. So basically, what this is saying is you're looking at what exponent would make, you would raise e to get back x. So by definition, if you had y equals ln of x, this is e to the y then equals x. So one more domain in the question. So it looks good. Find the domain of y equals the square root of ln of x. So multiple things are happening here. We are worried about the natural log of x. We can't have x give us a negative number for the natural log, but we also can't have the natural log, whatever that value is, can't be negative because of the square root. Kind of like the composition. This is kind of a composition of a composition where we have to worry about one domain and that output giving us problems for the other piece. And so a couple of things we need x to be greater than 0. Okay, well that fell out pretty fast, right? But we also need and ln of x has to be greater than 0. Okay, so how do we approach this? Well, that's basically, I'm looking at when is my function either, where is my function of natural log of x bigger than 0? So let's find out then when is ln of x equal to 0? Because that would be my x-intercept, and then I know graphically it's either changing on either side of that possibly, or maybe just touching the x-axis and dipping back. And so let's use the definition. So this is saying e to what power, or e, no it doesn't say that, it says e, our base is e here. E, this is our exponent of 0 is equal to x. So what's e to the 0 power, or anything other than 0 raised to the 0 power is 1. So this is technically like a critical number. Well, we know x has to be bigger than 0. So we don't even have to look at anything to the left of this. We want to know what's happening though in between 0 and 1 and what's happening after 0 and 1. Okay, so choose a value. So let's say x is 0.5. So if we plug this in here, we want to see if this is a true statement or not. So is ln of 0.5 greater than 0? Well, what is this saying? If we go back to definition, ln of 0.5, this is saying e, we're going to raise this to what power to get back 0.5? How am I going to get a 0.718, which is e, approximately? What am I going to raise that to give me a number that is less than 1? If I plug in a positive number in here for y and I raise it 2.718 to a positive number, that's going to give me something bigger than 1. If I raise this as a number between 0 and 1, because it has to be in here, Shoot. The only thing I can raise this to 2.718 to get a number that is less than 1 is if this was a negative exponent. So in order for this to happen, y would have to be negative. Because that would bring this this would bring that 2.718 down into the denominator. And so would that give us, is that going to be bigger than 0? No, that's false. But if you choose a number over here, so let's choose x equals bigger than 1, so x equals 2. So looking at this, we have the natural log of 2. Is this greater than 0? So this is saying e to what power? I'm surprised. Okay. Okay, that's okay. Ellen, if this is saying e to what power is equal to 2? If it's a negative number, it's going to bring it down to the exponent. It's going to make it smaller. It's going to make it, yeah. If I take a radical, though, of a square root or some root, then I could get this to 2. So I'm kind of doing some reasoning without using my calculator. But if we plug this into the calculator, natural log of 2, you get that this is approximately 0.7. That is greater than 0, and so this is true. And so for our domain for both, it has to be, x has to be greater than 0, and the natural log of x has to be greater than 0, and that's when x is 1. So our domain is not including 1 to infinity. Okay, so graphing. Logs. Well, it depends on your base. Is your base bigger than 1, or is your base of your log between 0 and 1? Same with what happened with our exponential. So if you have y equals log base b of x, where b is greater than 1, you'll get the following shape of your graph. So you end up having a vertical asymptote instead of a horizontal asymptote. So we have a vertical asymptote at x equals 0. Our domain, which we had already stated before above because we knew what the domain and range of our exponential were, and we knew it was spot for our inverse function. Our domain looking at this has to be bigger than 0. And our range, again, we're hitting all of our y values from negative infinity to infinity. And this is strictly increasing. And notice that we have a point here, 1, 0, On our exponential, remember, we always had a point at 0, 1. And so flip them, x and y flip for a function and its inverse. So that makes sense too. If you look at the graph of y equals log base b of x, but b is between 0 and 1, it's a reflection, but this time it's a reflection of this across the x-axis instead of the y-axis. And so it comes down and it looks like this. So again, almost identical vertical asymptote. At x equals 0, domain is still 0 to infinity. Our range is still negative infinity to infinity, but this one is strictly decreasing. Okay. So if it said graph y equals log base 2 of x. Okay, so this is where knowing the general shape, and you should know the general shape again of these graphs, exponential and logs, and we should be able to apply transformations of graphs on these. And so here, I'm just kind of wanting the general shape. My base is bigger than 1, so I know that this general shape is like what it is. Let's say I didn't know that and I wanted to plot points. Well, if we can rewrite this in exponential form, we can do that. So by definition, the exponential form is your base is raised to what? Your what is the y. So we have our base is 2 raised to the y is equal to whatever we're taking the log of, x. So normally when we plot points, we usually plot values in for x and we determine what y is. Here we can plug in values for y and determine what x is. That's one way to do it. That's the way I normally teach it. Now I'm thinking if we kind of just think about this with exponents, we could choose values of x really easily. Maybe let's do it that way, just to get used to what log is. So basically, we want to choose values of x that we know what the exponent is. So I know I want to choose something here that is 2 raised to a power. That could figure out what y is easily, and getting enough points will help. I know, again, x has to be greater than 0, so I'm not going to choose any number bigger than 0. Well, how about, let's try 1 first. So 2 raised to what power would give you back 1? Well, 2 raised to the 0 power is 1. So here, on this case, if I plugged in 0 for y, notice, I get 2 to the 0, which should give me back the x of 1. Okay, what about 2? So if x is 2, so if x is 2 here, this is saying 2 to what power would give me back 2? Well, 2 to the first power is 2. Where here, if I did it this way, I would have chosen my value for y. So if I plugged in 1 for y, 2 to the first is 2. My x value is 2. 4 is another base, 2. So 2 squared is 4. So my y value is 2. 8 is base 2. So that would be a 3. But let's also think about fractions. What value, what exponent of 2 would bring that down to the denominator and make it 1/2, which is -1. I just want to show you just this one example that we're going to get that general shape that I had stated above. And so if we plot our points, we have a point at 1, 0, which was one of the points that was special and I said we would get. We have a point at 2, 1. We have a point at 8, 3. We have a point at x is 1/2, y is -1. And so if we draw this connecting our points, we get that general shape I had said we were going to get above if our base was bigger than 1. Okay, so now that we kind of got an idea of what the shape of our logs are, you can apply this again using transformations of graphs. And so let's look at one of the following. So if we wanted to graph y equals, how about the negative of log base 2 of x? So let's just think the only thing that's happening, so our parent function, or the function that we're going to perform operation transformations on, let's say it's g of x equals log base 2 of x, what we just graphed. So you think to yourself, how do I manipulate this equation to get a negative in front? Well, I'd have to multiply my y value by a negative. So it's swapping my y values. Swapping my y values is a reflection across the x-axis. So if I graphed that, it's not going to affect my point at 1, 0. But this piece below is now going to be above the x-axis here. And this piece above is now below the x-axis here. So let's go a little bit further. What if it was y equals still that negative in front of the log, so negative log base 2, but this time we have a negative in front of the x. So not only did this first negative reflect the graph originally, log base 2 of x, across the x-axis, this negative here, this reflects y equals a negative log base 2 of x across the y-axis. Sorry, it changes my value of x, so this is a reflection across the y-axis, So if I take this graph that we just graphed, negative log base 2 of x, and flip it across here, I know what the general shape is going to look like. Oops. Pretend it's a mirror image. If I talked about my domain and range, well, the negative log base 2 of x, my domain and range did not change from what log base 2 of x was. But notice here, my range didn't change, flipping it, but my domain has changed. The values I plug in for x have to be negative, which makes sense because I have to take a log of a negative number. The negative of a negative is positive. Okay, so we were looking at logs and we were trying to figure out what exponent gave us the base. But you should be able to solve a log equation where the unknown is other than what it's equal to. So for instance, if you had log base 5 of x equals 3. Well, what a log is 5. Our answer is the power. Our exponent is 3, has to equal what we're taking the log of, which is x. So if you can't see it, rewrite in exponential form. By definition, those are equivalent, and then this falls out right away. We can just cube 5. 5 times 5 is 25. 25 times 5 is 125. So x is equal to 125. We need to make sure our answer is part of our domain. So with logs, make sure your answer is part of the domain. What is? We have to have a log. X has to be greater than 0. And this occurs 125 is greater than 0. Shoot. So what if we had log base 5 of x squared plus x plus 4. That's what we're taking the log of. And this is then equal to 2. So 5 to what power gives us this back? Well, 5, it's equal to 2. So it's 5 squared has to give us this back. Okay, so simplify. 5 squared is 25. 25 is equal to x squared plus x plus 4. Quadratic equation, set it equal to 0. Subtract 25 on both sides. So we get x squared plus x. 4 minus 25 is negative 21 is equal to 0. Unfortunately, there's no two numbers I can think of that multiplies to negative 21 and adds to 1. And so we're going to need to use our quadratic formula. So x is equal to negative b. So negative 1 plus or minus the square root of b squared. 1 squared is 1 minus 4 times a is 1 times c is negative 21 all over 2 times a is 1. So 4 times 21, that's 84. We have two negatives. So it's plus 1 plus 84 all over 2. So 1 plus or minus, negative 1 plus or minus the square root of 85 all over 2. Oh, that one's in the back. Okay, I cannot have a log of a negative number. So I'm not sure, I'd have to go back and plug this in. It would make sense more if I plug this in a decimal form instead of fractions with rationals. So x is approximately, so let me just get approximate. If we do -1 plus the square root of 85, and we take that answer and we divide it by 2, we get about approximately 4.1. If we looked at -1 minus the square root of 85, we took that result and we divided it by 2, you get back approximately -5.1. So we just need to make sure that x squared plus x plus 4 is greater than 0. So if we plug in 4.1 in there, that was my original, wasn't it? Yeah, x squared plus x plus 4. If we plug in our original 4.1, well, 4.1 squared plus a positive, that's positive. So we're good with 4.1, that's gonna work. The negative number, if I take -5.1 and I square it, and then I subtract off 5.1 plus 4, well, let's just think about this a little bit logically. -5 times -5 is 25. 25, that's gonna be bigger than what we put in here, the subtracted off. So this is also going to give us a number that is bigger than 0. And so we're okay. If you plug in these values for x, it works that they're in our domain. And so the solution, those are approximate values that I was using, but our solution is, exact solution is the following. So this is actually interesting. E raised to the 2x plus 5 is equal to 8. So I'm kind of surprised they have that in there right now because we haven't kind of looked at solving logarithmic equations or properties of logs yet. But it is interesting. What do we know about this? Let's go backwards. Let's go back to exponential or logarithmic form. So we know that this is our exponent, right? And so for our logs, that's what our answer was. Our answer is our exponent. We see that E is our base. And so for logs, if we have base E, I guess I'm going to write it as log base E, but really that's a natural log of, and this is what we're taking it of, 8. Okay, let's solve for x. So this is really natural log. I've never looked at it this way, but I've seen students do it this way before and thought it was interesting on how they were doing it. And now this is the first time I've seen a book do it this way. So I'm kind of curious, and this is a different textbook, like I said. Okay, so remember log base E is natural log. And so this is natural log of 8 equals 2x plus 5. Well, we're trying to solve for x. So we're going to rewrite in log form. And now solve for x. So we could subtract 5 on both sides, so we get the natural log of 8. Be careful because that 5 is not with that 8. So minus 5 is outside of that natural log, is equal to 2x. Divide both sides by 2 to get x by itself. So we get that x is equal to ln of 8 minus 5 all over 2. And that would be our exact answer. Okay, so before in the past, and I'm going to teach this in a second, I'd have to use rules of logs. I know taking a log of something can bring my exponent down front. But this is really cool. I kind of like how they do this. So maybe let's do one more. So what if it had been 8 times, oops. Okay. So 8 times 10, all raised to the 2x minus 7 is equal to 3. So I want to rewrite this in terms of an exponential form, but it's not quite in that form yet. That we can, I want to rewrite this in the form of a logarithm, but I can't do that quite yet because this is not quite an exponential form. I have this coefficient of 8 in front of my exponential piece. And so let's get rid of that coefficient and we can divide both sides by 8. So this gives me 10 raised to the 2x minus 7 power is equal to 3/8. Okay, so putting this in logarithmic form, the base is 10. And so I know this is just going to be a log. I don't have to write my base 10. The answer, base is 10. My answer is the exponent. So that is the 2x minus 7. And this is what I'm taking the log of, 3/8. And so now I want to get x by itself. And so if we add 7 to both sides, we get log of 3/8 plus 7 equals 2x. And now divide everything through by 2. So x is equal to log of 3/8 plus 7 all divided by 2. Okay, so we're going to get some more practice on solving these log equations or exponential equations in the rest of the sections. So let's move on. That was 6.4. 6.5 is continuing with logs, but giving you properties of logs. So properties of logs. Oops. Okay, so a couple things. If you have log base A of 1, well, we kind of already talked about this. What could we raise some base 2 to get back 1? Well, we could raise something to 0 to get back 1. So one of the rules is log base A of 1 is 0. Another rule says that if you have log base a of a, what can we raise a to get back a? Well, we can raise a to the first power to get back a. So let's go even a little further. What about log of a raised to the nth power? So this is saying a raised to what power is a to the nth? Well, a to the nth power, right, is a to the nth. Okay, so those are a couple rules. Another one, which is a log this exponent. So a raised to the log of a of m equals m. And log, I already did this one. Okay, so I've always known this one, but I've never seen the proof of it or never. And this book showed the proof of this, and it came out really fast and easy. So let's look at the proof of this. And a lot of your mathematics, the further you go on in your courses, the more you're going to be proving why you can use these rules that you're given. And so let's prove a log of a of m actually equals m. Okay, well, let's get some stuff that we know. So let f of x equal a raised to the x power. Then we know that the inverse function, logs and exponential are inverses of each other, is log base a of x. If functions are inverses of one another, then we also know that if we take the composition of f and f inverse of x, this has to equal x. Okay, well, let's do that. Let's look at the composition. So this is looking at f of the composition of my inverse function, which is this log base a of x. Now I'm going to go back to my function of f of x, and wherever I see an x there, I'm going to replace it with that log function. And I'm just going to bring down my right-hand side. This is equal to x. So if I go back in on my left, and I go back in wherever I see an x, so I have a, put a parentheses, and now go back and put in log base a of x in there. This is equal to x. Okay, we're almost there. Then let's just say m is equal to x. So if I just go back in here and I go in and wherever I see an x, I replace it with m, I got back what I wanted to show. So then I have a log base a, I see an x, replace it with m, is equal to, I see an x, replace it with m. Okay, so once you've shown something, and it's kind of satisfaction to be able to draw this square. The square represents that you're done with your proof. Yeah, your book does use it. Their x's, or not their x, their square is filled in. So that could be nice too. Okay, so a couple more rules that logs have. What was the other one? Another one is that if you take, well, that was this one. This one we can prove here. By, again, using the exponential and its inverse, but take it to the opposite direction. So you would use f inverse of f of x. I'm not going to go through that proof. Rules of logs. Okay, so logarithms are really helpful in mathematics when you get further. If you have, and a lot of times you have variables in your exponents, and so being able to use rules of logs to bring them down is helpful. Also, you might have some complicated logarithmic function, and if you can rewrite it as a simpler sum or difference of logs, that's going to help you be able to solve something in calculus so much faster than if you left it as a complicated logarithmic function. But also going from a string of multiple logs down to one log is also very important and helpful. And so this property of logs, you're going to use a lot later on. And so it says that if you have some log, it doesn't matter what the base is, base b of, let's say, a, and you are adding some log of the same base, base b of something else, capital B. And this is the same thing as log base b of a multiplication of what you are taking the log of the first times what you are taking the log of the second. So log base b of a times b. So here's the example of a sum of logs going to a more complicated logs, or more complicated logs going to a simpler sum of logs. Another one is if you have subtraction in between the two logs, we can rewrite this. If it's subtraction in between, it's division. So what you were taking the log of the first divided by what you were taking the log of the second. And you're taking the log of that. If you have log base b of a raised to some power, maybe call it m, this is the same thing as m times log base b of a. Okay, so this is the one I've been using pretty much all my mathematical career to figure out what my variable is for an exponential function that I couldn't solve for. So actually, maybe. So let's maybe look back at one of those ones that we just did, or something similar to, where we would have rewritten it. If I can find it. So e raised to the negative 2x plus 1 is equal to 13. So this is where I would use property 3 to solve for my variable. We were just showing this by rewriting this in logarithmic form and being able to solve for it. And so let's use this property of logs so that we can bring down our base. So because my exponent, my base here is e, I'm going to use natural log. So let's take the ln of both sides of the equation. We can do this because it's an equation. So what we do of one side, we can do of the other. We're basically taking a composition of this one side and a composition of the other side. Okay, let's think about definition of logs. I can actually use this property, or let's bring this down and bring it down. My exponent in front. There's more than one term, so I'm going to put parentheses around that whole thing. So my exponent is negative 2x plus 1. Put that in parentheses. I have natural log of e. Is equal to the natural log of 13. Well, natural log of e. This is saying natural log of e. Natural log is log base e. So this is saying e to what power is e? Well, e to the first power is e. All times negative 2x plus 1 equals natural log of 13. I don't know what I'm going to raise 2.7182 to get 13. So I'm going to leave it as natural log of 13. So I want to isolate my variable. So let's subtract 1 on both sides. So we have negative 2x then is equal to natural log of 13 minus 1. And then divide both sides by negative 2. We get x equals natural log of 13 minus 1 all over negative 2. I'm just curious. Let's do it the other way. I wonder which way is faster. Other way is you would look at what log you are using. We're using a natural log. Our answer is our exponent of 13. This is so much faster. Now subtract 1. Natural log of 13 minus 1 equals negative 2x. Divide both sides by negative 2. And get x equals natural log of 13 minus 1 over negative 2. Well, maybe it's not. But either way, you get the same result. Okay, so let's go back to those properties and just be able to rewrite them. So if you had log base 2 of 1 over x plus log base 2 of 1 over x squared. And this says write each expression as a single log. So in between my two logs is addition. Addition between logs tells me multiplication. And so this would be then log base 2 of 1 over x times, when I was taking the log over here, 1 over x squared. So let me just simplify that a little bit. So this is the same thing then as log base 2, 1 over x times x squared is x cubed. Let's go the opposite direction. So let's rewrite log of big bracket, then x cubed square root of x plus 1 all over x minus 2 quantity squared. They tell us that x is greater than 2. That must be part of the domain. And we want to rewrite this as a sum or difference of logarithms, express powers as factors. So write each expression as a sum or difference of logarithms, express powers as factors. Okay. So a couple of things, we're going to have to do a lot of things here. We see division. So let's break down the division. Division tells us we can break down logs with a minus sign. And so we're going to look at the log of our numerator minus the log of our denominator. Okay, so log of our numerator is log. I need an x cubed times the square root of x plus 1. And then we have minus the log of our denominator, which is x minus 2 quantity squared. But I noticed that this first log can be broken down some more. Notice that in between the two is multiplication. So we have multiplication of the x cubed and the radical. On my second log, I notice I have a exponent, and they didn't want any exponents. And so I notice I can also bring my exponent down in front. So, and this is a plus. So I have log of my first, so log of the x cubed, plus log of the second, so log of the square root of x plus 1. If you don't mind, I'm going to rewrite that as x plus 1 to the 1/2 power, minus I just brought my power down front to log of x minus 2. Okay. Notice that I still have exponents. I have an exponent of 3 here, and I have an exponent of 1/2 here. And so we can bring down those exponents as factors in front. And so doing that, we get 3 times log of x plus, bring our exponent down, 1/2 log of x plus 1 minus log of x minus 2. So we just rewrote this as sum and difference of simpler logs. Okay, if you do this, you're not going to get credit on your exam. You cannot distribute. This is log of something. This is an exponent. We can't distribute this log inside a parentheses like this. We can't say this is the same thing as log base b of a plus or minus log base b of.
Isn't the last one supposed to be minus 2 log?
Yep. Bring that 2 down. Thank you. So it doesn't make sense to distribute when you're thinking of the answer being the exponent. It's the exponent would get this back. Okay. So I think that's a great spot to take a break. And then we'll do a couple more problems of solving and looking at using these properties to solve logs and exponentials, and hopefully a few word problems. And then we're done with this section or chapter, which was my whole goal, was to get done with that today so we can spend a little bit longer, maybe one section slower to get through new material for you guys. Okay, so let's meet back here at 2:50, so 20 minutes. Great. Let me turn on the light. Okay, so solving logs and exponential equations, and then your book splits it up into multiple sections of word problems. And so looking at solving problems that deal with interest rates and exponential growth and decay. Okay, so I was kind of worried about that. I accidentally didn't pause the recording when I went to break. It doesn't look like it. Okay, so now we're going to use those properties of logs to help us solve these logarithmic and exponential equations. There was one other property that I forgot to mention, which is also helpful when you're solving these logarithmic equations. That is basically if you have some log of the same base of A equals another log of the same base of B, then we can say then that A has to equal B. We can go backwards. If A is equal to B, then we can take the log of both sides of our equation and say that those are equivalent. Okay, so solving logarithmic equations, basically your goal is to either get everything to one side of your equation and rewrite it as a single log. And once it's a single log, we can rewrite it in exponential form. And it usually falls out right away that you can see how to solve it. Or if you can manipulate it where you have a single log equals a single log, then you can drop the logs and say what you're taking the logs of are equal to each other. So I'll pull some examples out. When we're solving log equations, one other thing, you would have to be careful because our solution or our answer might not be a solution because it might not be in the domain. We only can take logs of positive numbers. So if we have the following, let's say -2 log base 4 of x is equal to log base 4 of 9. Okay, so these are the same base. And I almost have a single log equals single log. I can't have this -2 in front, but I can take care of that. We can rewrite it as an exponent. So let's move this up as an exponent of x. And so doing that, we now get log base 4 of x raised to the -2 power equals log base 4 of 9. So by this rule above, we have x to the -2 power equals 9. There's multiple ways you can solve this. We can rewrite that with a positive exponent, 1 over x squared, and solve it that way. We could raise both sides to a power, because power to power is multiplication. That would make our exponent 1. So I notice if I multiply -2 by -1/2, so if I raise both the power to the -1/2, that would also work. I'm going to rewrite it as a positive exponent and go that route. So 1 over x squared equals 9. If I multiply both sides by x squared to clear my fraction, I get 1 equals 9x squared. Divide both sides by 9, we get 1/9 is equal to x squared. Take the square root of both sides. And so x is equal to plus or minus the square root of 1/9. Rules of radicals. We can look at the square root of the numerator over the square root of the denominator. So we get 1 over 3. Again, we want to check. I can't have a log of a negative number. And so if I go back to my original equation and I see here, if I plug in that -1/3 here, that's a log of a negative. And so -1/3 is not going to work. And positive 1/3 would work. And so x is just equal to 1/3.
Wait, so why isn't the -1 again? Sorry.
It can't be -1/3 because by definition of log, you can only have a log of a number that's positive. So there's no way that I could take 4 and raise it to some negative or some power and get back a negative number. And so whatever you're taking a log of has to be positive.
Okay, thank you.
So let's say you have log base 4 of x squared minus 9. So x squared minus 9 is in parentheses. Then we have minus log base 4 of x plus 3. And this is equal to 3. Okay, so I noticed that I can't manipulate this because I have a constant of 3. I have a term in here that doesn't have a log. So I can't manipulate this like we were doing before, a log equals a single log. And so now we want to use the property that if we have a string, a sum, or difference of logs, we can rewrite it as a single log. Our minus in between those two logs tells me that I can rewrite it as a single log using division. And so I would have log base 4 of my numerator, which is the first of what I was taking the log of, x squared minus 9, all over the second log of what we were taking the log of, which was the x plus 3, equals 3. Okay, so I can jump in right away and I can rewrite this in exponential form, or I can factor and simplify first, it doesn't matter. Let's just go back and rewrite this in exponential form. So it says take your base. Our answer is our exponent of our base. So this is 4 cubed equals, notice that x squared minus 9, that's a difference of 2 squares. So let's just factor this at the same time if that's okay. So our numerator could be factored as x minus 3x plus 3 all over x plus 3. So notice this is nice because I can simplify my fraction, right, by simplifying and canceling x plus 3's. 4 cubed, 4 times 4 is 16, and 16 times 4 is 64. So 4 cubed is 64, is equal to x minus 3. Okay, x by itself, we can add 3 to both sides. So we get x is equal to 67. Check if we plug it back in here. If I square 67 and subtract 9, that's bigger than 0, so I'm okay for that piece. And 67 plus 3 is okay because it's positive. So our solution is 67. So this one, we have log base A of some variable x plus log base A of x minus 2. This is equal to log base A of x plus 4. So again, you want to rewrite this as a single log on one side of the equation. I notice I don't have any terms in this equation that doesn't have a log in it. So we could manipulate this to be a log of the same base equal a log of the same base, and we can just set what we were taking the logs of equal to each other. I notice if I ended up rewriting this in exponential form, actually it would work also. And we could do that if we wanted to rewrite that as a single log equal to 0. And then we would take a raised to the 0 power, which actually is 1. And we could solve for x there. It would be faster if we just did the log equal a log though. So rewriting that one side as a single log, you have a plus in between. Plus tells you to do multiplication. And so we have log base A of the first, which was x, all times the second, x minus 2. And this is equal to log base A of x plus 4. So a log equal to a log, same base, so we could just drop the logs and say, well then x all times x minus 2 then has to equal x plus 4. So notice this is quadratic. Let's distribute. We have x squared minus 2x is equal to x plus 4. Quadratic, get everything to one side, subtract x. We have x squared minus 3x. Let's subtract 4 equals 0. Factor. So two numbers that multiply to -4 and add to -3 is a -4 and a +1. So we can factor it as x plus 1, x minus 4. Set each factor equal to 0 and solve for x. So x plus 1 is equal to 0 when x is -1. And x minus 4 is equal to 0 when x is 4. So check. Notice if we plug in -1 in for x up here, well, log base A of -1, that's a log of a negative number. So we cannot have that. If we look at 4 though, log base A of 4, that's positive. 4 minus 2 for this is 2, that's positive. And 4 plus 4 is positive. So plugging in 4, it's always a log of a positive number. So we're okay. X equals 4 is the only solution. So about natural log x minus 3 natural log, actually minus 3 square root of ln of x plus 2 equals 0. So very interesting. We can't combine these two. I have this minus here. I can bring this exponent up, but the problem is that the square root. The square root, that natural log is all underneath that. And so there was one rule. You notice how we couldn't take the natural log and distribute it to a sum or difference. Another thing that gets students is this. So if you have natural log of x to the 1/2 power, or the square root of this, does not equal ln of the square root of x. Or another thing to say, how about ln of x to any power of b is not the same thing as the natural log of the x raised to the b power. And so you cannot take, if you have a natural log, that whole natural log is raised to an exponent, you can't bring that down front because they're not identical. Okay, so knowing that, let's rewrite this a little bit. And I noticed that this actually can be rewritten in quadratic form by using some substitution. So kind of similar to what we had done at the beginning of the semester, except now we're going to have to manipulate it with logs. So here we have a natural log of x minus a 3. I'm going to rewrite this as a natural log of x, all raised to the 1/2 power plus 2 equals 0. So I'm trying to make this look like a quadratic. I know power to power is multiplication. So if I have natural log of x, and that piece is all raised to the 1/2 power, I'm also trying to make this first term to look identical to this middle term. So when I use my u substitution, it's a quadratic. So power to power is multiplication. So this natural log x to the 1/2 power squared. Because 2 times 1/2 is 1. That would get us back to this original term above. So minus 3 all times natural log of x to the 1/2 plus 2 equals 0. So let's go and make this a substitution. So u equal ln of x to the 1/2. Or if you want to write it as u equal to the square root of the natural log of x, either way. So wherever we see that, we're going to go back in and we're going to replace it with u. So I see it here and I see it here. Oops. So rewriting that with a u in there. So we have u squared minus 3 times u plus 2 is now equal to 0. And so looking at this isn't too bad. So it looks like it's pretty easy to factor. Two numbers are multiply to positive 2 and add to negative 3. So that would be a negative 2 and a negative 1. So u minus 2, u minus 1 equals 0. Set each factor equal to 0. So we get u is 2 and we get u is equal to 1. We don't want u. Our original equation started with x. And so, but we know that u is equal to the natural log of x. Oops, square root of x. Square root of natural log of x. So we're going to have two separate equations. We're going to look at it when 2 is equal to the square root of natural log of x. And we're going to look at it when 1 is equal to the square root of the natural log of x. So we need to get x by itself. We don't want that square root there. And so we can square both sides of our equation to get rid of the square root. We just have to be careful because we're squaring both sides of the equation. Now we could be causing extraneous solutions, answers that don't work in our original. Maybe at the same time we can square this equation also. So that first equation we have 2 squared. So this gives us 4 is equal to the natural log of x. By definition, this is equivalent in saying our natural log of x is base e. This is saying our base e is being raised to that 4th power is x. Okay, so we got x is e to the 4th. Square both sides of your equation here. And so squaring both sides of the equation here, we get 1 is equal to ln of x. So by definition, this is saying e, our answer is our exponent to the first, is equal to x. So let's go back and check. So there's multiple reasons why we have to check, because we squared both sides of our equation and because our original equation had logs in it and it's affected by a domain. Let me just see if I can pull this down here. It'll make it much easier. Oops. That's not what I want. ln of x. Wrong button. Oops. Yay. Okay, so we're going to go back and we're going to check. It actually isn't as bad as we think, because the natural log of e is always just its exponent. And so here we have the natural log. I'm going to go put parentheses in wherever I see an x. So we have the natural log, parentheses, minus 3, square root. We have the natural log, parentheses, and then a plus 2. Does this really equal 0? Oops. Get the wrong button. So now go in and plug in e to the 4th power. And if you plug in e to the 4th power, turn it. Okay, sorry. I was trying to be fancy and copy and paste again, so I didn't have to rewrite it. That's probably taking longer. What are we doing? We're going back in and plugging in e to the 4th. Okay, so natural log of e to the 4th, it's saying e to what power is e to the 4th? Well, e to the 4th power is e to the 4th, so this is just 4. So it's 4 minus 3 square root. Again, natural log of e to the 4th is 4, square root of 4. And then plus a 2 out here. Is this truly equal to 0? So 4 minus, well, square root of 4 is 2. 2 times 3 is 6. So 4 minus 6 plus 2, is that equal to 0? And it is. So e to the 4th works. Now let's go back in and see if e to the first works. So plugging in, so natural log, put in a parentheses wherever you see an x in your equation. So minus 3 square root natural log, put a parentheses where you see an x, plus 2 equals 0. So now we're going to go in and we're going to plug in e wherever you see an x, or parentheses. So natural log of e, well, e to what power is e? E to the first power is e, so this is just 1. Minus 3, well, this is just 1 again. Square root of 1 is 1. Plus 2, is this equal to 0? Yeah, 0 equals 0. Okay, so they both work, and we have our solution. Is the set e and e to the fourth. So that was actually kind of a good review of being able to manipulate certain equations to be able to rewrite them in terms of quadratic equations to solve. So let's say you had 2 raised to the negative x power equals 1.5. So solve each exponential equation, express irrational solutions in exact form. Okay, so we're trying to solve for x here. We can rewrite this in exponential form, or logarithmic form, like I showed before, or we can't manipulate these spaces to be the same. And if that was true, that's the first way I would go about it. Can't do that, so I want to take the log or the natural log of both sides. And so if I took the log, and it doesn't matter in this case, if my base was either e or base 10, or either of these, I would choose one of the other. This case, it's not, so I technically like to use natural log just because it's a little shorter to write, but it doesn't matter. So if I took the natural log of both sides of this equation, now I can use the property of exponents to bring our exponent down, of logs and exponents. So this is the same thing as negative x all times our natural log of 2 equals the natural log of 1.5. So notice we can get x by itself if we divide both sides by negative natural log of 2. So x is equal to negative, I can pull that negative out front, natural log of 1.5 all over natural log of 2. So don't get confused. We can't cancel out natural logs. This is really an answer, an exponent. What do you raise e to get 1.5? What do you raise e to get 2? Those don't cancel. Also, don't get confused. We have a division here, but this is division of a natural log of the numerator over the natural log of the denominator. When we had division, we broke it up into 2 separate logs. With subtraction, it was natural log of a fraction, and then we could break it down. And then we're done. So this is the exact form. You can throw it into the calculator to get an approximate. So if you had 2 raised to the x plus 1 power is equal to 5 raised to the 1 minus 2x power. Okay, so here's the case where I couldn't use that definition of logs, I don't believe, because I have exponents in both of my exponential pieces. But I noticed that I can use my rules of logs to bring down those exponents, and then my variable won't be in an exponent anymore, and we can manipulate it to solve. So either take the natural log or log of both sides. It doesn't matter in this case. So if we took the log of both sides, so log of 2 raised to the x plus 1 power is equal to log 5 of the 1 minus 2x power. So bring our exponents down front. Notice I have parentheses around there. So if you don't have those parentheses down there and you bring this down, you would have technically the wrong thing. You would be saying, basically, I didn't have these parentheses, so let me bring it down without the parentheses on the other one. 1 minus 2x log of 5. This technically right here on the right-hand side is saying I'm only multiplying this log of 5 by the negative 2x. And so you guys are getting higher in math that you're going to get knocked off for things that aren't mathematically correct and points docked. So make sure that you have parentheses around that. Okay, so we're trying to get x by ourselves. Doesn't look very pretty. Technically though, these logs of a number, that's just a constant. That's just some constant that's ugly. It's some 10 to what power is 2. But so we can treat it like a constant. Or well, even we could treat it like if it was a variable. Let's distribute it. So we have to distribute it to both terms. And so we would get then x log of 2 plus 2 log of 2 is equal to distributing our log of 5. So log of 5 minus 2x log of 5. Okay, so looking at this equation, let's look at our x terms with x. Notice that all values of x are just raised to the first power. So we got a linear equation here. Notice that there's only 2 terms, groupings, that have x in it. And so just like we would solve for linear equations, we want to get all the terms with x to one side of the equal sign and all the terms without the x on the other side. So I'm going to add this 2x log of 5 to both sides of the equal. So we have then x times our log of 2 plus 2x log of 5 is, so at the same point, let's move this positive 2 log of 2 over to be with the constant of log of 5. So if we subtract 2 log of 2 on both sides, our other hand side would be log of 5 minus 2 log of 2. There's multiple terms with x. They're not like terms. They're not the same log, same base, but not the same log. So use the trick to factor what you want out of there. So if we factor out an x, from both of those terms, you're just left with, inside parentheses, log of 2 plus 2 log of 5 equals log of 5 minus 2 log of 2. Get x by itself, divide both sides by that parentheses. So x is equal to log of 5 minus 2 log of 2, all divided by what's in the parentheses, log of 2, plus 2 log of 5. Okay, so here's another instance where I would not give you many points on an exam if you start canceling things out here, because they can't cancel. It's not strictly multiplication in between. And so we get our solution. Doesn't look very pretty. Some of these could be written a little differently. So I technically could write this a little differently, which means the same thing. What if I brought this 2 up first, our coefficients as exponents? I could rewrite this as x equals log of 5 minus log of 2 squared, which is 4, all over log base 2 plus, bring that square up. That would be log of 5 squared is 25. But this is also equivalent. I could rewrite this as a single log. Minus tells me between 2 logs, I can rewrite it as log of 5/4, all over log of addition, 2 times 25, 50. So there's multiple different forms that these answers could be written in, and they're all equivalent. You're okay with leaving it like this, unless it states in the directions. Then it wants it maybe as a single log, I don't know. But I can't go any further. I can't rewrite this as a single log. I can't cancel those logs again. Okay, so let's jump into some word problems. Okay, so they look at financial math is one section, is what they call it. Basically, and we've looked at this before, interest problems, simple interest. You should know is equal to PRT. So this is the interest that you're earning, or maybe not earning, paying, depending on if you're borrowing or investing. So P is equal to what is called your principal, which is the amount invested or borrowed. T is equal to the amount of time, usually in years. R is equal to the interest rate. Where the percent is written in decimal form. Okay, compounding interest. Okay, so this is where your interest is being compounded multiple times, and maybe multiple times per year. So compounding interest, you're going to use the formula. This actually gives us the amount that you're getting back. It doesn't give us the interest that you earned, but you can figure that out. Of P, all times 1 plus R over N raised to the NT power. Again, almost, yeah, it is all identical. P is equal to the principal, so the amount that invested or borrowed. R is equal to your interest rate. N, the only other thing, is N is equal to the number of times compounded a year. So sometimes things compound continuously. I mean, you can think of it as breaking it down into minutes, down into the, then seconds, fractions of a second. And so it's continuously to compound and getting interest. So compounding continuously it ends up that A is equal to P all times E raised to the RT, where E is that irrational number. T again is time, R again is interest rate. The other part, which is the next section, and I'm just going to go through and just give you the formulas. It's basically the same thing that we have here. It's exponential growth and decay. These are exponential functions. So exponential growth and decay are always in the form A of t. I can just say A, but that's again our amount. This t, I could have been putting t in here. Our variable represents time, and our amount is dependent on how much time we have in there. A sub t is equal to, and here they put A sub 0, e to the kt. Couple things here. A sub 0, this is our initial amount that is given, or maybe we have to find. K equals our growth rate. So it's almost identical to our compounding continuously. It's just that we have K instead of R. This is decimal form of that growth rate, not percent form. T again is time. Depending, actually I should say K is growth rate or / decay rate. So maybe something isn't growing exponentially, maybe it's decaying exponentially. And so depending on if K is positive or negative depends on if we have a growth rate or a decay rate. If K is bigger than 0, it's growth rate. And if K is less than 0, it's a decay. Okay, so let's pull some examples. Okay, so let's look at some savings. Okay, so I'm just going to read through the problem, then we're going to go through, we're going to pick out important information and write it down, and then kind of figure out equations that we know that will help us. Okay, so on January 1st, Kim places $1,000 in a certificate deposit that pays 6.8% compounded continuously, and an interest in a passbook account that pays 5.25 compounded monthly. How much does Kim have in the passbook account on May 1st? Really? Okay. Okay, so let's go back through here. Kim places $1,000 in a certificate of deposit that pays 6.8% compounded continuously and matures in 3 months. Then Kim places the $1,000. Okay, maybe I didn't read this correctly the first time. Then Kim places the $1,000 and the interest in the passbook account that pays 5.25% compounded monthly. How much does Kim have in the passbook account on May 1st? Okay, so we have $1,000. She's going to invest it in a certificate. A certificate of deposit that pays 6.8%. Compounded continuously. And matures in 3 months. Okay, so right there, questions go up in my head of what does that mean, mature in 3 months? Does that mean that's as long as she can keep it in there? And then after that 3 months, she just takes what she has? So I might have to go back and look at that and see if the book talks about that. But I also noticed just with this piece of information, I can set up an equation. It's cluing me in that she's doing this compounded continuously, and it matures in 3 months. Okay, compounded continuously. Right here, this is saying I'm going to use the formula. A is equal to P e to the RT. So I know in here that my amount that I'm investing is $1,000. Then I have E, my interest rate, which is 6.8%. Well, I need to convert that into decimal form of the percent. So move our decimal over twice. So this is to the 0.068. This is where the 3 is getting me, the 3 months. T is normally in terms of years, and so we need to convert 3 months in terms of years. So we can do that. I know 3 months. Well, I know there's 12 months in 1 year. I need these to cancel. So this is 3/12 equals a year, which is 1/4 of the year. Or put it in decimal form, which is 0.25. Okay, so my amount T is 0.25. Okay, so this is just that amount for the first 3 months. So it matures after 3 months, and then let me reread what it says. Then Kim places 1,000 and the interest in a past book account that pays 5.25% compounded monthly. So how much does Kim have in the past book account in May 1st? So this is on January 1st. 3 months later, so this is the amount that she's going to have on, well, she has to have it in there for 3 months. So January is to February 1st is 1 month. February 1st to March 1st is 1 month. And March 1st to April 1st is 1 month. So this is the amount that she gets on April 1st. Then it tells me that she's going to take this amount and she's going to invest that amount. So the original amount, the $1,000 plus the interest she just got from this certificate. So then Kim places $1,000 and the interest in a passbook account that pays 5.25% compounded monthly. Okay, so now, so she invested at 5.25%. Tells me it's compounded monthly. And we want to know the amount on May 1st. Okay, so let me first think about that May 1st. So let's see how long she's actually investing this amount that she got from her certificate into this passbook. Well, if she got back her money, let's say April 1st, it matured, and she goes in and she invests it right away, she has how many months? So she has April, May, well, I guess she only has 1 month in there. So how much after 1 month is there? After 1 month. We need to put this again in years. Okay, so 1 month. Well, I know again that there is 1 year and is equivalent to 12 months. And so this is equal to 1/12 of a year. So T in this case is going to be 1/12. Compounded monthly, I got to look at that formula. Compounded monthly, so the amount that you get back is equal to your principal, which is what we just got back here, all times 1 plus your interest rate, R, over how many times it's compounded a year, N times NT. So monthly, that's telling me that N is the number of times compounded a year is 12 times. 5.25%, so we know what R is. R is equal to, in decimal form, 0.0525. And we know what T is. So we can go back in and we can plug this in. So our amount is equal to our principal, which I didn't simplify. I'm just going to put it in here right now as what our principal was up here. Let's see if I can do it. Let's see if I can grab it. So it's equal to our principal, which was the amount that we had gotten before, which is this, all times our equation. Oops. Yeah, that's kind of cool. I changed the color. Oops, sorry. All times, not equals. 1 plus our, again, interest rate, which we said was 0.0525. All over the number of times it was compounded a year, which is 12. This is all raised to the NT. So N, number of times it's compounded a year, was 12 times time. And time was only 1 month, which was 1/12. And so we can start simplifying. Okay, so on my calculator, I am going to put in E. When I put it in E, it automatically gives me, in my calculator, an exponent. I need parentheses around this whole exponent that I'm putting in here, 0.068, then times 0.025, and then I have to close off the parentheses of that whole exponent. And if I multiply that answer by 1,000, this first piece that I get this is $1,001.70. Why would we want to invest that just to get back $1.70? Okay, anyways. That is all times this piece in here. And so this piece in here, notice that our exponent gets to 1. And so I have all times 1 plus, so 0.0525 divided by 12. And add it to 1. I get back 1.004375. I'm going to multiply that back to the answer that we had above, 1001.7. So the amount that she has back is $1,006.08. I did something wrong. That's where I'm going to need to go back and look at that mature rate. It's telling me that the answer so $1,021.60. Okay, so we're pretty much out of time for class, so let's stop there. I will go back and look at my work. I'll also look into what it means to be matured by 3 months to see if that affected our answer any. And I'll let you guys know tomorrow. I'm sure you're going to be on the edge of your seats waiting for that answer.